Hello, I'm a final year PhD student at the University of East Anglia, and I'm going to focus on how we've used textural studies of juvenile clasts to gain insights into the ascent dynamics of a small volume trachytic eruption on Ascension Island. So what are these eruptions and why are they important? Well, they typically only output less than a few kilometres cubed of material, but they are found all over the world in a range of settings. And despite being small in volume, they often exhibit multiple explosive effusive transitions, and so the hazards they present to nearby communities are varied. These eruptions are often poorly preserved, either due to erosion or subsequent overprinting by later eruptions, and where it is preserved, the stratigraphy may not be well exposed. This also precludes accurate determination of VEI, as calculations of erupted mass or mass eruption rate typically require multiple sample sites at a range of distances from the vent. Our knowledge of the physical properties of these melts has recently improved. The viscosity is much lower than calc-alkaline melts, they dissolve more H2O and H2O diffusivity is higher. These melts can also crystallize rapidly during ascent. Thus, the concept of kinetically reactive trachytic melts is beginning to gain some traction, and this has important implications for considering the types and timescales of the hazards produced by these eruptions. As these eruptions have the potential to rapidly change in nature, we must find ways to infer eruption explosivity and its drivers at a higher resolution. To do this, we've taken the example of the Echo Canyon eruption on Ascension Island in the South Atlantic. Ascension is approximately 19 kilometres west of the Mid-Atlantic Ridge, and the Echo Canyon deposits are situated in the east of the island within the Eastern Felsic Complex. The eruption deposits span an area of approximately 3.4 kilometres squared and record an initial explosive phase producing a pumice cone, an effusive phase which produced a dome and brecciated lava flow, and a final minor explosive phase which produced a pumice fall that mantles the underlying topography generated by the previous eruption phases. The deposits are cut by three valleys, shown in Map 2, Echo Canyon, Rainbow Canyon, and Spire Beach. These dissections enabled us to reconstruct the 3D geometry of the eruption and make detailed lithologic observations of the cone stratigraphy as the framework for our textural study. We focused our study on the pumice cone deposits, which we divided into lower, middle, and upper. The lower cone is comprised of dominantly clast-supported pumice fall deposits, while the upper cone is dominated by matrix-supported pyroclastic density current deposits, which contain sub-rounded to subangular pumice clasts. The middle cone represents a transitional phase between the two, as it contains a higher proportion of ash, but clasts are dominantly still angular in nature. In the upper cone, we see the occurrence of obsidian clasts and obsidian breccia for the first time in the stratigraphy. We examined juvenile clast textures from the Echo Canyon eruption products, all of which contain the same distinct macrocrystal population, 2 to 5 mm alkali feldspars and clinopyroxenes. 5 main pumice clast types were identified in the lapilli population based on vesicle textures observed in hand specimen. 2 groups dominated by equant vesicles, 2 dominated by elongate vesicles of different sizes, and 1 classified as dense. These observations were backed up by evidence from thin section images of representative clasts. Macrovesicular equant clasts showed evidence of coalescence without shear, whereas in clasts with elongate vesicles, shearing had introduced coalescence, but vesicle collapse was not a dominant feature. Dense clast exhibited extensive evidence for vesicle collapse, e.g. thick glass walls, dense bands, and irregular elongate vesicle networks. Clasts of obsidian breccia are comprised of angular fragments of juvenile material including pumice, obsidian, and whole and fragmented crystals. We measured the density of 116 to 32 mm pumice clasts from 6 units of the pumice cone. We then categorized each clast into one of the 5 identified textural groups and plotted these as percentages. We can see that patterns in lithologic characteristics throughout the cone coincide with changes to juvenile clast texture and vesicularity. I'm just going to highlight a couple of key points. In the plot of clast textures, you can see that the sheared clasts, groups 3 and 4, increase in abundance in Unit 3, which has a high modal vesicularity and the narrowest vesicularity distribution, while Unit 4 sees an influx of dense type clasts and a much broader vesicularity distribution. In the field, these 2 units are thickest and are massive, lacking ash horizons or lenses of fine material, and thus may represent establishment of a stable plume, perhaps at the peak of the eruption. Unit 9 was sampled from within the transition to PDC deposits and also has a very broad vesicularity distribution, explained by the highest abundance of dense clast observed in the eruption deposits. We can see that significant shearing is not established until the peak of the eruption and is followed by an influx of dense clasts and coincides with the transition towards PDC formation, indicative of partial or total column collapse in the later stages of activity. As the physical processes controlling a vesicle population in an ascending melt also influence explosivity and the nature of fragmentation, if we assume the pumice clasts represent the state of the melt at the point of fragmentation, we can infer changes to these processes using the vesicularity distributions of the resulting pumice population. Muller et al. Collated data from felsic and mafic eruptions with established VEIs and interpreted their vesicularity distributions in this way. For fragmentation, narrow distributions reflected bubble interference and rupture, while broad distributions reflected bubble overpressure. High modal vesicularities reflect a higher volatile concentration at the point of fragmentation, whereas low values reflect extensive outgassing, vesicle collapse, and densification. They also found that bimodal distributions record multiple outgassing pathways or histories, such as in dome-forming eruptions. We then plotted vesicularity distributions for all the explosive units from the Echo Canyon eruption and compared them to the eruptions of known VEI. We can see that units 1 to 3 have very similar narrow vesicularity distributions that have higher modal vesicularities. Unit 3 has the narrowest distribution, and all three closely match the curve produced by the Krakatoa 1883 eruption, which was classified as VEI 6. Units 4 to 11 are broader, displaced to lower vesicularities, and in some cases are almost bimodal. None of the units, however, closely match the mafic explosive eruptions, despite low viscosities associated with trachytic melts. We thus infer a shift in fragmentation mechanism from bubble interference to transient fragmentation between units 3 and 4, and an increase in outgassing and vesicle collapse, which is supported by the increased abundance of sheared clasts in Unit 3, which give way to an increase in dense clasts in Unit 4. Muller et al. Used the data they had collated to draw up a relationship between mean bulk vesicularity and VEI. We used this to place some constraints on the potential peak explosivity of the Echo Canyon eruption. When we plot the Echo Canyon deposits, we can see that units 1 to 3 align closely with that of the Campanian ignimbrite and the Krakatoa eruption. Vesicularity distributions between these units and the eruptions were similar, and the Campanian ignimbrite is trachytic, indicating that it is possible for these lower viscosity melts to display behaviors equivalent to a VEI 6 eruption. It is unlikely, however, that the Echo Canyon eruption would have sustained this level of intensity for a long period of time, as the later units do not have the same vesicularity distributions and we do not see the large volumes of material we would expect from a true VEI 6 eruption. Low viscosity trachytic melts have shorter timescales for melt reorganization and higher H2O diffusivities. This may have accelerated the development of an initial frothy magma and then later development of permeable networks, meaning that maximum explosive potential of a wet silica-rich melt such as this was only expressed for a short period of time. Additional complexity is evidenced by the obsidian and obsidian breccia clasts in the upper cone. Obsidian can form by melt densification through vesicle collapse due to permeable outgassing. Evidence of the initiation of this process is provided by the influx of first sheared and then dense clasts in the lower and middle cone. The presence of obsidian fragments within the pyroclastic density current deposits is thus not only a symptom of extensive outgassing, melt densification, and accumulation at conduit margins, but also contributes to plume densification and may have promoted plume instability in this late phase. Furthermore, clasts of obsidian breccia display features commonly seen in tuffosites and contain the distinct macrocrust population only found in the Echo Canyon juvenile material, indicating tuffosite formation occurred within material that had already begun to accumulate at the conduit margins. Obsidian tuffosites are the record of explosive degassing, and are thus evidence of a secondary outgassing pathway active at the transition to column collapse and the eventual explosive effusive transition. This may be reflected in the slight bimodality of the middle and upper cone vesicularity distributions. In summary, we interpret that at the peak of the eruption, marginal shear zones had developed, but bubble collapse had not yet initiated, and the explosive potential of the ascending magma, equivalent to that of a VEI 6 eruption, was only transiently expressed. Continued shear-induced coalescence then promoted permeable outgassing and bubble collapse, producing an influx of dense tight pumice clasts and facilitating melt accumulation and obsidian formation at the conduit margins. Tuffosite formation is recorded in obsidian breccia class and indicates secondary explosive degassing, which may have promoted plume instability, and later the explosive effusive transition. We have provided further evidence of the complexity of ascent and eruption dynamics for small volume trachytic eruptions, and propose that the physical properties of these melts may indeed facilitate rapid transitions in eruptive behaviour. The hazards produced by these eruptions are significant and varied, and are worthy of much further study. Thank you for listening.